Okay, this is Dr. Peter Wazalewski, Emeritus Scientist from NASA Goddard Space Flight Center. And you can read that as well as I can.
Anyway, thanks for the invitation. My topic's probably a little bit different than what I've heard so far today. And what you see here is actually a piece of ice floating in the water. And it's kind of a caricature of me, I think. Before I started working for NASA, I kind of roamed around the Antarctic ice cap. First trip being on a 1,000-mile traverse. And became fascinated with ice and snow. And so after working with moon rocks and meteorites and earth rocks with NASA, I'm finally back with ice. And you can see the color. And optically, ice has the lowest birefringence. Sandy told me never to mention birefringence in an audience where I'm presenting because nobody would understand what it meant. But I'm sure all of you do.
We're optics guys.
But it's got the lowest birefringence of any compound that man knows. And so as a consequence, you can actually play with relatively thick pieces of ice because, as you know, ice is kind of critical in that it melts easily. And all of my optical stuff started as a geologist using polarized light microscopy to look at thin sections of rock. And uniquely different are the rocks because you have different birefringence for every mineral that's in that rock. Whereas in ice, the color does only do the thickness.
Different mineral content in the ice?
Well, you would have them as an impurity,
versus, yeah,
and they
right.
usually would be very small. And if they were big enough, I would not call it ice. I hooked up with a Norwegian guy who makes musical instruments from ice. And so I put together a video that's on YouTube of his ice music and my ice pictures. Okay? And even now, on Facebook, most of my friends are art sculptors and people that play with ice, just to find out what's going on with ice in the world. If you look at ice in the Antarctic, you immediately know that you don't get ice by freezing water. You get ice by the metamorphism of snow. And you can see the way that mechanical history of that big chunk of ice happens, because you can walk from the seacoast to the center of Antarctica and never climb a mountain and be up at 12,000 feet. And you have meteorites falling all over the Antarctic ice cap, and they flow in the ice. And then when the ice encounters, the snow and then firn and then ice, based on density and the fact that the bubbles of air that are 10,000 or 20,000 years old are now trapped. So if you want to know the CO2 content of the atmosphere 200,000 years ago, you can actually find it in the ice cores. And the meteorites traveling with this glacial ice come into the Antarctic chain of mountains, the Transantarctic Mountains, and they can't push the mountains. So they just tilt upward, and out pops a meteorite. So how do you get artistic about this? Well, I started a winter camp in Lake Placid, New York, to use ice and snow to make teachers better science teachers. I hope I've succeeded to some extent. And I noticed that there were bubble patterns in the ice. So I asked this guy who's an ice expert, and he said, I have no idea what that is. So I made a thin section, and lo and behold, the petals appeared. And I said to myself, well, we know what color ice can give, and if we can essentially figure out how to make the crystals grow in different ways, control the growth patterns, then we can get something. is, for example, icicles. And you can immediately see how the icicles were put together by looking at the way in which the crystals of ice are arranged. The color is something added. And I don't know, let's see, is anybody here old enough to remember 1980 and Miracle on Ice? Well, one thing that amazed me is that the thickness of an ice rink is only about 1 1/4 to 1 1/2 inches thick. And it's quite amazing to me, after sitting there watching the U.S. hockey team skate across the top. I mean, it's amazing to me that hockey players can stay on their feet, because these guys are as big as football players, and they hit each other with the same intensity, and yet they don't fall down, and they're on ice skates. And basically, I published this on it was in the Goddard, I think it was on the Goddard front page a couple of years back, and it's probably the first picture of an ice rink cross-section of ice. And I got an email from Don Zamboni, who's the great grandson of Zamboni, who makes the ice preparing surface machines. And he, of course, is interested in better ice at lower cost. And so we talked a bit, and we almost worked together, but he wanted things to be very proprietary, and I really didn't feel at the time that I would enter into something like that. And but I finally told him, I said, I can tell you what your recipe looks like and recommend to what would happen if you made it this way or that way, but I can't tell you how to make the best ice at the lowest cost. But it was interesting because, and I never knew that, like, the white paint layer was kind of embedded down at the bottom, and then you kind of flood it, and you can see where the U.S. team practiced, and it's amazing. There's only this much ice is really severely damaged by all these guys having their practice.
They put paint on the ice?
On the ice,
wow.
Yeah. And then they cover it with more ice.
Wow.
So that otherwise it would be erased by skating across the top. And as I was drilling this 1 1/4 inch, this guy comes over and he said, "Hey, no fish down there." I hooked up with a guy who makes ice sculptures in Vail, Colorado, and I printed a Frizion. I call it Frizion's Frozen Vision, and I printed that on clear plastic, and I embedded that in clear ice, and that was part of Winterfest in 2010. And then a woman who was producing a show at the Peabody Essex Museum in Salem, Massachusetts. It was called The Art of Water. And so water is, you know the phase diagram, solid, liquid, and gas. and so the solid, liquid, and gaseous forms of ice were represented in this gallery exhibit. It's been going on for an entire year. And these are four of the different Frizion images that I let them have for this particular exhibit. The colors that you get from thickness, like here, the gradients. And you might ask, what is this? Well, this is the 6-inch diameter Petri dish. And fortuitously, it produced a beautiful pattern. Normally it doesn't.
Looks like things are growing there too. Were you freezing this as you went?
No. This would be, all of it would be in the process of melting.
Oh.
I'm going up end of April for a week or two, working in an icebox at the U.S. Army Cold Regions Lab. Krell.
Have you ever tried video or time-lapse photography as it melts to get a dynamic color show?
Not in color, but just the ice itself. I've done that, so hope to do some of that at the end of April. Because Tony Gao from U.S. Army Krell, actually it turns out that ever since the wall came down and people in the Middle East kind of act up, more effort is spent on sand and things like that than on ice. But he was the first guy to drill through 2,000 meters of ice to bedrock at Byrd Station in the Antarctic. And I met him in 1961 in the Antarctic. And so he's the guy that showed me how to make a thin section of ice. Actually, at the U.S. Army lab in Krell. So I owe all of this to the U.S. Army. Don't tell them though.
The secret's out.
Does the machine always cost $25,000, or are there cheaper versions of it?
There's probably cheaper versions, but this is a. But I'm sure there are cheaper versions, but I haven't really seen one. I mean, it lasts forever. It weighs so much; it's just solid steel, and the blades themselves cost, I think, $700 because they're used for shaving frozen biological specimens for microscopy.
Oh yeah.
And it's very effective.
How did you make the picture in the upper left? The void of color.
There's two ways you get no color. One is to have it too thin, where you essentially get first order gray, and the other is to have it too thick, where you don't even get colors like this. It'll be kind of super faint pastel colors. So you get no real color if it's too thin, no real color if it's too thick. So that range between about, I don't know, 1/4 of a millimeter and 1.5 millimeters is where you get the best color. And you can see the variety of shapes. And usually when I'm producing these, I produce them in clusters. When I figure out what I'm doing produces this, I keep doing this, and I get that until I get tired of it. Okay? And then at the end, I throw 1,000 away and keep 10. Okay? I say that the visual magic happens when water begins to freeze. And this creates the canvas, which is painted by the thickness and shape of ice crystals observed in polarized light. And I've tried to. You actually came up with the best title for this, painting with light on a canvas of ice.
So yours.
And so on the left is how it all started. That's just me. The yellow is somebody from Australia gave me zinca, which is really colored zinc oxide. You've seen lifeguards with the white.
Yeah.
Just said every day I came out with a different color. You know, if you're in the Antarctic and you work 10, 12 hours, 14 hours a day, 7 days a week, because the sun never goes down in the summertime, you kind of get bored. So you try to entertain yourself. That's one of the ways you do it. And everybody says, oh, that's the best color yet. And on the right is where I am now. So I started with ice, and I wouldn't say I'm ending with ice, but I'm doing ice now. So full circle. So that's it. That's about ice from an artistic point of view. Any questions?